The time horizon, the amount of time it takes for AI to work on a complex task without any human help, is growing at a rate of about 10 times per year. So, for example, now in 2026, AI agents can complete complex tasks that would take a human about 1 week, and those AI agents are able to complete those jobs, those tasks, fully autonomously for 1 week straight. And that time that AI agents working on a task fully autonomously for 1 week straight, it will increase by a rate of 10 times by next year, within the next 12 months. So by next year, 12 months from now, AI agents would be able to complete tasks, digital tasks, without any human help for 10 weeks straight, fully autonomously. And this will continue with each passing year. It The time it takes for AI agents to work fully autonomously without human help will grow at a rate of 10x every year. And uh, this is true for digital tasks, the white collar jobs such as programmers, lawyers, um, in any basically any job that can be done on a computer with a keyboard and mouse. Those types of jobs, AI is improving at a rate of 10x in terms of the time length, time horizon, time it takes for to complete the tasks fully autonomously. Whereas for physical tasks, such as performing surgeries, driving a car, and plumbing work, construction work, those tasks, jobs, AI is improving at a slower rate because of the nature of those jobs. Because with digital tasks, AI can run a simulation, can run a trial and error of a specific digital task like a million times in 1 second. Whereas with physical tasks, it's not possible for AI to run a simulation multiple times within a short period of time because of the physical aspect of that job. But what is nice about AI is that AI, even for the physical tasks such as performing human surgeries, it's able to learn from just watching YouTube videos. So there are tons of videos on YouTube on various physical tasks, such as human surgeons performing surgeries on a human, plumbing work, construction work, all those physical jobs. AI is able to learn just by watching those videos, and 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 with each video that it watches, it's able to improve. And for the physical world, physical tasks, AI is able to improve in terms of the tasks, physical tasks that it can perform fully autonomously without human intervention at a rate of about 2 times every few years, meaning the length of physical tasks that the AI can do is doubling every few years. And this is, and we can see this with self-driving, fully autonomous taxis. We can see that self-driving cars are improving. They are improving, and they're driving more and more fully autonomously with each passing year. But it's not a 10x improvement every with each passing year compared to digital tasks that AI can do. Now I will show a PowerPoint presentation in which I explain how AI has been able to grow in terms of the length of tasks that it can do every year, about 10x every year. In my PowerPoint presentation, I have mentioned that it's roughly every 4 months, the length of tasks AI is able to do fully autonomously is doubling. A doubling in the length of tasks AI can do fully autonomously every 4 months equates to about an 8x, an 8 times growth in terms of the length of tasks AI can do. And this is approximately, on average, it's about every 3.5 to 4 months that the length of tasks AI is able to do fully autonomously is doubling. A doubling in length of tasks AI can do fully autonomously every 3.5 months is equal to about a 10x growth in the time horizon. Today we are diving into a critical analysis of the current state of AI capability growth. We will be looking at groundbreaking data from 2024 and 2025 that suggests the frontier of AI is moving significantly faster than previously thought. We've titled this the AI Capability Acceleration, doubling every 4 months, and we will explore how we measure this progress using the new time horizon metric. To understand where we are going, we have to look at how we've been measuring AI until now. For years, MMLU and superglue have been the gold standards. MMLU, which stands for Massive Multitask Language Understanding, tests a model's breadth of knowledge across 57 academic subjects, while superglue, which stands for Super General Language Understanding, evaluates complex linguistics understanding. However, as AI has evolved, these tests have reached their limits. MMLU consists of over 15,000 multiple-choice questions across 57 subjects, ranging from elementary science to PhD-level law and ethics. Its goal is to measure a model's breadth of knowledge, general knowledge, and its ability to reason across professional academic domains. Following this is superglue, a successor to the original glue benchmark, designed to test deep linguistic understanding and contextual inference. For a long time, these were the definitive tests for determining if a model had reached human-level understanding of written language. However, as we will see, these tests are no longer sufficient for today's frontier AI models. The most significant problem we face with these traditional benchmarks is saturation. Frontier AI models have essentially solved these tests, frequently scoring above 90% accuracy. When a benchmark is saturated, it hits a measurement ceiling and loses its ability to differentiate between the best models. Imagine trying to rank the world's best sprinters, but everyone is finishing within 0.01 seconds of each other. At that point, your stopwatch is no longer a useful tool for comparison. In the AI world, when AI models score in a narrow range like 90.2% versus 90.4%, those tiny differences are often just statistical noise or minor prompt variations rather than true breakthroughs in intelligence. Consequently, these tests have become ineffective for tracking the actual progress of modern AI development. The failure of traditional benchmarks isn't just about high scores, it's about what they measure. There's a critical difference between isolated skills and real-world agentic behavior. An AI model can ace a static test like MMLU but still fail spectacularly when asked to string those same skills together to complete a real-world task. Standard tests measure atomic intelligence, answering one question or solving one math problem in isolation. However, economically valuable work requires autonomy and persistence over sustained periods. A model might know the answer to a question but lack the persistence to manage a project that takes a human an hour or even a day to complete. To address these limitations, the 50% task completion time horizon metric was introduced, which specifically measures an AI's capacity for sustained multi-step autonomy. When we apply this new time horizon metric to data from 2019 through early 2025, we see a remarkable exponential trend. For 6 years, the capability of AI models doubled roughly every 7 months, a rate significantly faster than Moore's law, which sees transistor density double every 21 months. However, the most recent data from late 2024 reveals a critical shift. When we fit our model exclusively to the newest frontier AI releases, the doubling time shrinks dramatically from 7 months to approximately 4 months, or just 104 days. This suggests we are entering a phase of super exponential growth. This acceleration is likely due to technical improvements in agentic architecture, such as self-correcting mechanisms and multi-tool orchestration, suggesting that AI is becoming more proficient at assisting in its own research and development. The impact of moving from a 7-month doubling rate to a 4-month doubling rate cannot be overstated. Under the historical 7-month trend, it was projected that AI would be able to autonomously complete tasks requiring a full work month of human effort, roughly 160 hours, sometime between 2029 and 2031. However, with the current 4-month acceleration, that timeline is pulled forward to as early as 2027. This creates a 2.5-year gap, removing nearly 30 months of preparation time that we previously thought we had. We are entering a period of non-linear capability jumps that exceed historical precedents. Even if growth slows slightly, the data suggests that autonomous week-long professional tasks are an inevitability by 2026. To ensure these findings are robust, researchers developed a 170-task logarithmic benchmark suite. The goal was to move away from single-focus tests and instead measure AI across a wide spectrum of human effort and complexity. This suite is grounded in human labor units, meaning every task was rigorously timed by human experts, with durations ranging from mere seconds to over 30 hours of professional work. By using human time as the anchor, we can directly compare AI performance to the actual time a human professional spends on economically valuable projects. This allows for a much more practical and predictive assessment of AI's impact on the workforce than traditional academic tests ever could. The 170 tasks are divided into 3 specific suites. First is HCAST, the Human Capability Aligned Task Suite, which features 97 tasks lasting from 1 minute to 30 hours. This suite is the core measure of agency and persistence on non-coding multi-step projects. HCAST consists of 97 distinct tasks that vary in length from 1 minute to 30 hours of human professional time. HCAST serves as the central measure for agency and persistence on multi-step non-coding tasks. It specifically shifts the evaluation focus from just answering questions to completing entire projects. It is designed to test an AI's ability to plan complex sequences of actions, manage state over a sustained period, execute long multi-step workflows. The suite includes a wide range of high-level professional work such as high-level reasoning, complex data manipulation, strategic problem solving, and interaction with external systems, including the web and various APIs. The SWAA suite, which stands for Software Atomic Actions, consists of 66 tasks lasting 1 to 30 seconds, capturing the fundamental building blocks of software engineering. These atomic actions, like writing a short function or finding a bug, are essential subroutines for larger projects. Benchmarking these ensures that the AI can handle the basic steps required for success on longer tasks. The suite consists of 66 precisely defined tasks. Unlike the more complex agentic tasks, these are designed to reflect actions that take a human professional between 1 second and 30 seconds to complete. By focusing on this narrow time window, the researchers can establish a high-resolution baseline for the absolute building blocks of technical work. The tasks are defined as atomic, meaning they are single-step actions that cannot be broken down further without losing their professional utility. Specific examples include code generation, writing a single specific short function or a few lines of logic, and debugging, identifying and fixing a single obvious bug within a small code snippet. And finally, environmental setup, which involves executing a minimal set of commands to initialize a coding environment or run a script. Finally, we reach the Research Engineering Benchmark, or RE benchmark, which represents the absolute ceiling of current AI capability. This suite is composed of 7 high-complexity tasks, each requiring approximately 8 hours of expert human effort to complete. Unlike simple tests, these are multifaceted, open-ended problems that mirror the work of senior ML engineers. The scope includes implementing novel algorithms from scratch, replicating research findings, and performing deep data analysis. The strategic value of RE benchmark is clear. It is a primary indicator for AI-driven research and development. If an AI model can succeed here, it proves it can assist in developing the next generation of AI. This capacity is a major driver of the 4-month doubling acceleration we are currently witnessing. Let's define our core metric, the 50% task completion time horizon. This is the human task duration where an AI model has a 50% probability of total success without any human help for tasks that take 1 hour to complete. It is vital to understand that this is a binary metric. There is no partial credit. Success means 100% completion, fully autonomously. If the AI completes 99% of the work but fails at the very last step, it is recorded as a total failure. We measure it this way because in a professional setting, a nearly finished task still requires a human to step in and fix it. Think of this as a tipping point for reliability. If a task is short, 5 minutes for example, the success rate is very high, around 95%. If a task is long, 5 hours for example, the success rate drops toward 5%. The time horizon identifies the specific point where the AI's success is a toss-up. It moves the conversation away from how much does the AI know and focuses on how long the AI can be trusted to work autonomously. To conclude, we are witnessing a fundamental paradigm shift in AI. Because traditional benchmarks like MMLU have reached saturation, the industry must pivot to the 50% time horizon. This metric is the only way to accurately measure real-world autonomy and the ability to execute complex projects rather than isolated knowledge tasks. The data is clear. We have moved from a 7-month doubling rate to a 4-month doubling rate. This super exponential acceleration, driven by breakthroughs in self-correction and tool orchestration, is dramatically compressing our timelines. What does this mean for the real world? It means the preparation time for society and policy has been cut by 30 months. Month-long autonomous projects are now projected for early 2027, and week-long tasks are an inevitability by 2026. We must transition immediately from observation to the proactive strategic integration of agentic AI systems. The time to adapt is now.